Hi, I'm Prithvish, and I'm going to talk about rendering scenes for simulating adverse weather conditions. This is a research project done at Indian Institute of Information Technology, Guwahati. So, the state-of-the-art object detection schemes perform very well in normal weather conditions, but many of them fail when it comes to adverse weather conditions. To deal with this problem, adverse datasets should be trained and tested on object detection schemes, but available datasets didn't have many images in such weather conditions. Also, the lack of balanced datasets results in poor detection performance. Hence, we propose a novel approach to render uh, rainy and foggy datasets to address the described problem. In the rain rendering scheme, a new model is proposed for rain streak generation. The streaks are drawn with the help of the equation y equal to mx plus c, and with x1, y1, x2, y2, the coordinates of the start and end point, and m being the slant angle. Further, to add the blurry and low light effect of the rainy day, blur using average filter and enhancing contrast with the following equation are done. Also, scaling down the lightness channel values of HSL color model to add the said effects. Finally, the input image is converted to RGB color model, followed by blending of rain streaks uh, and the input to obtain the rainy scene image. The fog rendering scheme is based upon the atmospheric scattering of light, where we render heterogeneous foggy effects with the Perlin noise. At the beginning, input image is pre-processed to render some dull effects. Then the depth map is computed, and the depth map evaluation is done with from monocular images input to the pre-trained ResNet uh, architecture with encoders initialized with weights of the pre-trained ImageNet. The image is then normalized between 0 and 1, followed by the inverse depth map and grayscale conversion. This inverse depth map grayscale image is passed to the Perlin noise generation segment, where the noise generating function takes the gradient vectors of the boundary points and the grid points and finds the dot product, followed by 3D Perlin noise estimation using the equation this with J being the number of dimensions. The amount of noise with increases with depth. The generated noise is then blended with the original image to get the foggy scene image. Also, to define user controlled amount of fog, as uh, we say that it is fog coefficient or omega, to increase or decrease the amount of fog. Some of the experimental results of rain rendering with different illuminations are shown, and also some foggy results are shown with different fog coefficient. Next is the comparison made with different approaches, and the proposed method for rain and fog rendering are shown in the slide. Also, to support the comparisons made, mean opinion score is calculated, taking 20 users from different disciplines in the ratio of 1:1 male to female, and are asked to rate on the scale of 1 to 5 on 100 images. These users were given images in pairs to rate them, but they were not told which images are from which scheme. The user input plot and the mean opinion score are shown in the slide for rain rendering and fog rendering scheme. Thus, in this work, we generated realistic fog and rainy images in order to fulfill the lack of balanced data set. Perlin noise distribution depends upon the depth map evaluation. Thus, it is proved experimentally that using MOS, our method outperforms other existing schemes. Thank you.